Have you ever wondered how your radio magically tunes into your favorite station, ignoring all the others? Or how your TV picks just one channel out of thin air? The secret often lies inside a tiny but powerful setup called a Series RLC circuit. It might sound like a secret code, but it's actually quite simple. R, L, and C are just letters that stand for the three amazing electronic parts that make up this circuit: the resistor, the inductor, and the capacitor. These three components are like the superheroes of the electronics world, and when they team up, they can do some truly incredible things. Let's break down the name. A circuit is just a path for electricity to flow, like a racetrack for tiny energy particles. Series means that our three superhero components are connected one after another in a single line, holding hands in a row. So, a Series RLC circuit is simply a path where electricity must travel through a resistor, then an inductor, and then a capacitor, all in one go. Understanding this simple layout is the first step to unlocking the amazing science that powers so much of the technology we use and love every single day. It's the foundation for filtering out noise and tuning into specific signals. Why are these circuits so important? Well, they are fantastic at picking and choosing. Imagine you're at a crowded party where everyone is talking at once. An RLC circuit is like having super hearing that allows you to focus on just one person's voice and tune out all the rest of the noise. In the world of electronics, signals are like those voices. There are radio waves, TV signals, and Wi-Fi signals all around us. RLC circuits help our devices grab the exact one they need to work correctly, which is a super important job in our busy, high-tech world. To really get a feel for how these circuits work, seeing them in action is the best way to learn. That's why diagrams and even cool animated images can be so helpful. They can show the flow of electricity and how each part of the circuit does its job. Visualizing the path helps make these abstract ideas feel much more real and a lot less intimidating. Think of it like a blueprint for an amazing electronic gadget. Seeing the plan makes it so much easier to understand how everything fits together to create something that works. Let's get to know our three heroes one by one, starting with the resistor. A resistor is like the traffic controller of the circuit. Its main job is to slow down the flow of electricity. Imagine water flowing through a pipe. A resistor is like a narrow section of that pipe that makes it harder for the water to get through. It resists the current. This is super useful for protecting more sensitive parts of a circuit from getting too much power at once. It helps keep everything balanced and safe, ensuring the electricity flows at just the right speed. Next up is the inductor, which is a bit like the circuit's energy saver. An inductor is usually a coil of wire, and it has a very special talent. It hates sudden changes in the flow of electricity. When the current tries to change, the inductor stores energy in a magnetic field to fight that change. It's like pushing a heavy merry-go-round. It takes a while to get it started, and once it's spinning, it takes a while to stop. This property of resisting changes in current makes inductors perfect for smoothing out electrical signals. Our third and final hero is the capacitor. If the inductor stores energy in a magnetic field, the capacitor stores it in an electric field. Think of a capacitor as a tiny, super fast charging battery. It can soak up electrical energy and then release it very quickly when needed. It's made of two metal plates with a gap in between. Electricity can't flow across the gap, so instead, energy builds up on the plates. This ability to store and release charge allows capacitors to block steady, direct current, but let changing, alternating current pass through, which is a crucial skill in many circuits. When these three components are connected in series, they create a fascinating team dynamic. The resistor is constantly using up energy and creating heat. The inductor and capacitor, however, are constantly trading energy back and forth between them. The inductor stores energy in its magnetic field, while the capacitor stores it in its electric field. This amazing energy-swapping dance is what gives the RLC circuit its unique and powerful capabilities, especially when it comes to dealing with different types of electrical signals. Now that we know our players, let's see how they work together as a team. When electricity flows through a Series RLC circuit, each component puts up a fight against the current. The resistor's opposition is called resistance. The inductor and capacitor also have their own types of opposition, called reactance. When you add up all this opposition from the three components, you get the circuit's total opposition, which has a special name, impedance. Impedance, represented by the letter Z, is like the total difficulty level for electricity trying to get through the entire circuit. Calculating impedance isn't as simple as just adding three numbers together, because the inductor and capacitor are like opposites. The inductor's opposition, or inductive reactance, gets bigger as the electrical signal's frequency gets higher. Frequency is how fast the electricity wiggles back and forth. On the other hand, the capacitor's opposition, called capacitive reactance, gets smaller as the frequency gets higher. So, one component likes high frequencies, and the other likes low frequencies. They are in a constant tug of war, and the resistor is just there, providing the same level of resistance no matter the frequency. This is where the real magic happens. Because the inductor and capacitor react to frequency in opposite ways, there is one special frequency where their oppositions perfectly cancel each other out. This sweet spot is called the resonant frequency. At this exact frequency, the only thing left opposing the electrical current is the plain old resistor. This means that at the resonant frequency, the circuit's total impedance is at its absolute minimum. The circuit suddenly becomes super easy for electricity of that specific frequency to pass through. This effect is incredibly useful. By choosing the right inductor and capacitor, engineers can build a circuit that has a very specific resonant frequency. This allows the circuit to act like a gatekeeper. It will let signals at or very near its resonant frequency pass through with ease, while strongly blocking signals at all other frequencies. This is the fundamental principle behind tuning. The circuit resonates with the desired signal, amplifying it, while rejecting all the unwanted noise. It's a beautifully simple yet powerful way to filter the electronic world. So where can you find these amazing RLC circuits in your daily life? The most classic example is inside an old-school AM/FM radio. When you turn the tuning knob, you are actually changing the properties of a capacitor inside an RLC circuit. This change adjusts the circuit's resonant frequency. When the circuit's resonant frequency matches the frequency of a radio station's signal, that signal is allowed to pass through and get amplified, and you hear your favorite music. All the other radio stations, broadcasting at different frequencies, are blocked. It's like finding the one key that opens a specific lock. This same idea applies to so many other technologies. Your television uses RLC circuits to tune into a specific channel. Each channel is broadcast on a different frequency, and the tuner in your TV selects the resonant frequency that matches the channel you want to watch. They are also used in signal processing and filter circuits. For example, in a stereo system, crossover networks use these circuits to separate the audio signal. They send the high-frequency sounds to the small tweeter speaker and the low-frequency bass sounds to the big woofer speaker, giving you rich, clear sound. Beyond entertainment, RLC circuits are vital in communication systems, like cell phones and Wi-Fi routers. They help to filter out interference and ensure that you are sending and receiving a clear signal. In power supplies, they are used to smooth out electrical power, converting a bumpy alternating current into a smooth direct current that sensitive electronics need to operate correctly. They are the unsung heroes working behind the scenes to make sure our digital world runs smoothly, without all the static and noise that would otherwise interfere with everything. Ultimately, Series RLC circuits are a perfect example of how simple scientific principles can be combined to create powerful and essential technology. By understanding how a resistor, an inductor, and a capacitor work together, we can control electricity with incredible precision. These circuits allow our devices to listen for specific instructions, ignore distractions, and perform their jobs better. From the music we listen to the shows we watch, and the way we communicate, RLC circuits are quietly working to filter our world, making our technology smarter, more efficient, and more reliable every single day.